Hey, welcome to the slope and equation of a line. What's this map doing here? Are you lost? Ah, no. I put it there to show you the grid system. Let's have a look at how maps use a grid to describe points. Here we are. We would have a scale down here perhaps, or some labelling down there, and across here another one. And that's a grid type system. So if we're coming to try and describe this point, we would say how far along there you had to go and how far this way. So you can describe all points. And you've seen this before, but the sort you've seen before was founded by Descartes and Fermat, two French mathematicians who used similar thing. And look at what I'm doing now. I'm making Adelaide the centre of the system, and I'm going to call this the X direction and this the Y direction. So if you're at any point on this grid, I can describe for you to get to another point. Where might you be? Well, let's say you're up here at North Adelaide, and we could say, well, what's your X value? That could be something like -1. And what's your Y value up here? That could be something like, what's the scale look like, about 5. So this would be the point now on our grid, X number first, remember, -1, 5. And then if you wanted to come across to Kent Town, I think there's a great school at Kent Town. There is a great school at Kent Town. And this would be maybe, that's about 4, isn't it? 4, 1 maybe. So this is the point, X number first, 4, 1. So we could describe how to get from one place to another. We could also find the distances, I reckon, between these 2 points, and lots of stuff like that. Let's have a look at the sorts of things that we've done before on this grid. Come down with me here, and here we have a grid, and there are two French mathematicians, as I said. The first was René Descartes, who went about drawing various shapes on a grid and trying to find the equation. So he went from shapes to an equation or a rule for the points to lie on that shape, and then de Fermat, around the same time, did it the other way. He made up rules or equations and then had a look at what the geometry or the shape was. So this is often called coordinate geometry, because it's a way of looking at shapes. So both doing that, way of looking at shapes on a grid and describing what was going on. So there's a big connection here in coordinate geometry between our algebra, our rules, and the geometry of the situation, what the shape looks like. So let's have a look at this grid now. What have we just been doing? Well, let's go 5 in the X and 5 in the Y. We would have this point 5, 5. If we then went, let's say over here, -2 in the X will go to there, and 3 in the Y. Up there we have this point here designated -2, 3. And what sort of things do we want to do with this system? It is named after Descartes. It's called the Cartesian coordinate system. Cartesian coordinate system. And you would have done some stuff with it before. And the sort of things, what might we do? Well, we could find the distance between these 2 points. Do you remember the formula for that? We might also find the slope of that line, the slope or gradient of the line. So let's list these things down. We could find the distance or length of the line, distance between the points. We could find the slope or gradient. And of course, you know the heading of this presentation is, of course, the slope and equation of the line, an equation of a line. So that's what de Fermat and Descartes were both looking at, all those sort of connections. And it's a good way of playing with shapes and geometry, because you can work with numbers and plot them out and see what the shape is doing. So I've just drawn here the things that we need to find the slope or gradient. You might remember here, as you go from this point over here to this point here, we have an x step, how far along in the x direction you go, and a y step. So you might remember that the slope or gradient of a line, usually given the symbol m, is the y step over the x step. That idea. And that's going to be important in applying straight line work to a practical situation. So let's go back and revise some of that stuff now. So come down with me and have a look here at a practical application of what we're about to do. And our screen clippings here are coming from Pearson's new textbook, Year 10. And so what we've got here is an application of, in physics here, how far, well, the distance a body has travelled with time. So here we are, distance against time. So it's a good physics application. Of course, what we're going to do is talk about the velocity or speed of the body with time. So there's three examples here: a bicycle, a car and a train. And can you see that if you're on a bicycle here, let's say you're starting at the same point on each of the three vehicles, in 4 hours you have travelled 20 kilometres. So there we have 20 metres, I think they've got here, isn't it? 20 metres. So with the bicycle, what would we say the speed was? It would be the distance over time for the bicycle would be 20 over 4, which is 5, it's in seconds, 5 metres per second. Oh, I see, yeah. So this is a slope, isn't it? It's a y step over an x step, but it's a contextual situation here where the y step is actually distance and the x step is time. And you can see where it's come up here to the car. Let's do the car for 4 hours. It's gone... sorry, not 4 hours, 4 seconds. It's gone 40 metres. So the car, the slope of that line, or gradient of that line, is the distance over the time, and that's twice as fast, 10 metres per second. We might also use this symbol. This is good, because when you're dividing by seconds, of course, let's have a look at that, the maths of that. M over S, right, dividing by S to the 1 is, using index or power notation, neg 1, so that's another way of writing it. And then finally the train's plot there, the plot of the train, the slope of that line or gradient of that line is going up to 4 seconds again. It's gone 60 metres, so it's travelling at 15 metres per second. So that's an application of the gradient or slope of a line. This is the y step over the x step, but when it means something practically. So that's going to be important later on. Can you see how crucial maths is in this analysis to other subjects? Let's go down now and have a look at the Pearson's definition. And we're saying here that obviously the points must have the x number first and the y number second, and you're going to then do this. The vertical rise, don't like the word rise much myself. I rather say that is the vertical step or the y step. And sometimes this symbol, and later on in maths you'll see this, is called delta y. Delta, Greek capital here, means change in, implies change in mathematics. So you might like to make a more sophisticated definition in a minute. Instead of horizontal run, that's a difference in the x's. This is the x step. You might like to make a definition that the slope or gradient is delta y on delta x, because delta in mathematics is used to mean changing. So that's our definition. So over here, what are we doing? We're getting the second y minus the first for the y step, and the second x minus the first. Now, it doesn't matter which way round you go. You could go the other way, but you must keep the x and the y in order. So you might be thinking about coming from this point, travelling down the line. In that case, you might think of y1 take y2 over x1 take x2. But the idea is the movement for these two must be in the same direction. Okay, so that's very, very important. All right, so let's go down and investigate this a little bit more. And here we have some properties that hopefully you've seen in your earlier maths, but it doesn't matter. It's catch-up time now. So the gradient is this, and what we're saying here is the gradient is constant for a straight line. Can you see that? No matter where you were on the straight line here, the x step or delta x and the y step, that ratio would be the same, okay, between any points. What are we saying there? If you move along the line, then the amount you move across and up must always be the same. How do we know that? Well, let's say it's not. Let's say in this little one here, for the x we move across the same distance, but we move up less. Uh-oh, it wouldn't be on the line, would it? So can you get a feeling, a good understanding of why the y step over x step must be the same along all points of a straight line? This is your example here. Here we are. If you're on the line and come across and you don't go up far enough, or maybe you go further on this point, it's not going to line up with your next point, is it? So they must line up, must have a constant y step over x step. So m is y2 take y1 over x2 take x1, and it must be kept constant to keep that line all lined up. So we'll have a look at that again in a minute. The gradient is positive if the y values increase as the x values increase. All right, well, what does that mean? Well, generally, in mathematics, on this horizontal axis, we label it x. You might change it for a contextual problem, like it was time, just back up there in our physics example. But we call this the independent variable, Okay, so what we generally do in mathematics is always speak about how that is changing, and then y is the dependent variable. We speak about how that changes dependent upon the exchange. So we always start off with statements over here, come over here. We always talk about what is happening when x changes, and we usually talk about moving this way on the x-axis. So as we increase the value of the independent variable, what is happening? That's what we say. So let's take this point here. As we increase the value of x, what is happening? Y is increasing. That's what we're saying. Okay. What about the line below here, the pink one? Let's go from the same point. As we increase x, what's happening? Y is decreasing. Do you get the idea? It's not hard to see. So that means the y increasing up here for this one would mean that delta y, or y2 take y1, would be a positive. And of course x is positive in both cases because we're talking about increasing the independent variable. But down here, y2 take y1 would be negative, because your second y is less than the first y. Okay, so we have the result now that this line is said to have a positive gradient or slope, and this one has got a negative slope or gradient. Not hard to see what's happening there. It's going up, it's positive as x increases, or it's going down as x increases. Try and get your head around that. This is important for increasing and decreasing functions in things like calculus later on. It's an exciting area of mathematics to look forward to. Let's have a look at these two down here now, a horizontal line and a vertical line. let's have a look at the horizontal line. That's this one here. It's parallel to the x-axis. Now let's try to work out its slope or gradient. Alright, let's take a point on the line here. So there's a point. This is the point 7 and 2. 7 and 2, and then a point out here maybe. This is the point 10, 2. Let's work out the y-step. 2 take 2 over the x-step. 10 take 7. It's 0 over 3. Hey, what happened there? Oh, I see. A horizontal line is horizontal because all the y's are the same. Its equation is actually y equals 2, isn't it? It's always 2. So you're never going to get a change in the y-step there. It's a flat line. So you get the answer of 0 on 3 is 0. So a horizontal line always will have a 0 slope or gradient. What about the other one over here? This one here, vertical line, has an undefined gradient. Well, let's try to work out. Here's a vertical line. Let's see if we can work out the slope or gradient. So same thing, y-step. Okay, well the y-step between any 2 points, well let's take this one up here. This is the point, what, 4, 8. And this is the point 4, 5. And let's work out its slope. Y-step, 8 take 5 over x-step, 4 take 4. Uh-oh, I think we're in trouble here. Dividing by 0. Uh-oh, is that always going to be the case on this line? Yes, because look at the line. It's always going through the point 4, 0. All the x's trace back in a vertical line to the same value. And so you're always going to get that 0 down there, and you know in mathematics division by 0 is not defined. So we have the result, a vertical line has an undefined gradient. Alright, let's do the last couple here. Can you see that if you want lines to be parallel like this, their y-step on their x-step must be the same. Otherwise one would be kinked across the other a bit. The y-step on the x-step must be the same for parallel lines. And now here's the special one. You may not have seen that. We'll be doing it again now anyway. If two lines are perpendicular, here we are, two lines are perpendicular at 90 degrees. This is a bit harder to prove. We'll have a look at it later on. That their y-step on their x-step has a special relationship. So if you call this one a slope of m1, then this one's slope, if it's m2, one is minus the reciprocal of the other. This over here. Or m1, m2 must equal neg 1. Okay, so we won't do the proof here, but we will touch upon that again later on. So the product of slopes being negative 1 means the lines will be perpendicular. Okay. Alright, so let's go and practice some stuff now and see what you think. Here's some Pearson's again here, and we're finding the gradient of these two lines. So they've actually drawn them out nicely here for us. So let's do the first one. Their steps are, list down the 2 points. I don't know that you need to do this every time, but then you would put down your formula. I'd start here. I think this is not something we do rise over run later in maths. We really call this more delta y on delta x. Okay, that sort of statement. And so it's the second y minus the first over the second x minus the first. And then we can cancel it down. So it's a fairly straightforward idea. So that came out to be a positive gradient. Do you realise? Yes, we'd give that a tick because as x increases, the line's going up, y is increasing. So that is a positive gradient. Let's have a look at this one over here. So we come down a little bit here and have a look. I just look at that now. So we state the 2 points. Okay, I've come off screen here. So point of neg 4, 4 and 2, 1, and it looks like the gradient is going down, or so slope of the line would be what, negative? The line's going down as x increases. Here's the other point, neg 4, 4, 2, 1. So let's start here. Second y minus the first, so that's going to be 1 take 4. Oh, that's where the negative's going to come in. 1 take 4 over x2 take x1. Must keep them in the same order. So it's 2, don't forget the take in there, take neg 4. And so we've got neg 3 over, watch this, 2 take neg 4 is 2 plus 4 is 6, so it's neg a half. Okay, so that agrees, that negative agrees with what we see up here. As x increases along here, remember we're always increasing the value of the independent variable and then looking at the response or how the dependent variable is changing. Oh, that didn't get, it's not going up, is it? As we go along, the line is going down. Alright, so as we go along, where's the y's? It's down there. So this has a negative slope or gradient. Okay, so thinking about that, it's a fairly simple idea if you remember that we always look at increasing x and observe the change in y. Okay, that's the way we handle it mathematically so that it's consistent each time. Increase the value of x, observe the change in y. Okay, your turn. You want to do some, here we are, got some problems here. I've used 2 sources. Pearson's had this group of problems up here, and I've got the answers next to you. Don't cheat, try and do it without looking at them. And then I've taken this from another publication, Hayes and Harris publications, a few extra problems there. And with Pearson's, we're going to go on with Pearson's, but I've split it into different sections, the slope and all the slope problems basically, and then the equation of a line problems. All right, you can pause the presentation now and have a go at those problems, because we're going to move on in a minute and look at the equation of a line. So pause it and have a go. I'm going to move on now. So coming down here, oh, what do we got here? I've been busy. Finding the equation of a line, question mark, question mark, question mark. What is that? AKA, also known as, what makes a line straight? I wonder if you've got any ideas about that. Why is a line straight? And this was what Descartes was looking at, saying, well, if we have a shape of a figure, what is the equation of it? And that's what we're going to do. We're going to follow in his footsteps here now. So there are 2 ways of actually looking at this. I'm going to try to answer this question by starting here with a y-intercept. I'm going to say, well, if the line is straight, it will come through this y-intercept at x is 0, y is 3. And as you go up here, what have we got? Well, we've got a y-step of, an x-step of 2, sorry, and a y-step up here to this point, which is what? 2, 7. So the step up is actually 4. We can count them off, 1, 2, 3, 4 units. So this y step is 4. So what are we going to do? Let's create the line. Let's say now we're going from the point 0, 3 to the point 2, 7. So what's our y's going to be? Well, we start off with the y value. We usually call it c. It's a y-intercept. Okay, so we're starting off with y equals 3. Now, every time we go up, so it's going to be added, what do? If we go up by 2, we get 4. If we went up by 1, we get 2. The same ratio, the same gradient. Every time we go up by 1, down here now, we go up by 2. So we will get the x value, right, and times it by 2, because the slope was 2. Y step over x step was 2, or 4 to 2, 4 to 2, cancels down to 2. Okay, so what does that mean? Is this always going to be true? If we went up 3 for x, and let's do that down here, down the bottom here, let's go up 3 for x. Oh, it's up to there now. on the line. So 3 produced a step of 6. Hey, this would work. If you multiply the x change by the slope, that's how much you have to go up on your line. This is what Descartes did. So it would be what? 2x plus 3. That's the way we can think about what makes a line straight. What is its equation? Okay, so can we generalise that? Generalising. So you can actually see why that rule must work. So y equals mx plus c, where this is the slope or gradient of the line, and this is the y-intercept. So that's a way of thinking about creating a equation or rule, or answering the question, what makes a line straight? Okay, so this is called the slope-intercept form. Okay, that's a way that of a straight line. That's the way that a lot of people think about it, and it's a good tool for doing it. Find the slope, find the y-intercept, and construct that equation. Right, now, Pearson does it slightly differently, so let's have a look at that. Now, let's go back to square one here. I'll just clean this up a bit here. Pearson says, well, okay, if you've got a point somewhere out here, we call it xy, because we want a general rule, and this point, we want to put it right on the line there. So this point here, xy, what must its x's and y's be to make the line straight, or keep the line straight? Well, if you took, let's say, the point that I was doing before, over here, 0,3, and we moved up here to find another point. So another point is, let's say, 1,5 now. Okay, so we'll start off here again, and we'll find the slope. So the slope is 5 take 3 over 1 take 0, which is 2, just as it was before. So we do the slope. So let's put that slope down. We've got 2. Now, that means if we took any point later out on the line and came back to this point or to any other point, the slope must always be the same. We just established that before. So let's write down the slope expression for any point. So this is any point on the line. So it's y step y take 5 over x take 1. So I'm doing it between these 2 points here now. Let's have a look here. I'm looking at the slope of the line between these two, between this one and this one, doing a y step on x step. And then, of course, we have, this would be a rule for all possible points x, y that wanted to lie on the line. Coming back to any known point must always give the slope of 2. We have worked out the slope of the line. Now we're describing what x and y must be for points to lie on the line. Let's now multiply both sides by x take 1. So here 2 times x take 1 equals y take 5. So 2x take 2 equals y take 5. And we should put implies there. Implies that adding 5 to both sides, 2x take 2 plus 5 is 2x plus 3. So we get the same answer with both methods. So one is called the slope-intercept form, and the other one is really called the general form. People use different names for it. Now, both have their uses. Later on in maths, as the expressions get a bit more complicated, or maybe the points aren't given in actual values, you have to work with general terms, the general form is probably the most useful later on. So we summarise it as m equals y take ya over x take xa. In other words, what we're saying is we take a known point, xa, ya, like we did here, 5 and 1 were the 2 values, and work any point back to that, a general point on the line coming back to that point. So you might use both of these, I think, now. You might have been introduced to it with mx plus c. But I think having a go with both methods is a good idea. All right, are you happy with that? You might have to pause and go back and think about those two. There are two distinct ways now of finding the equation of the line. Obviously, they give the same answer. Let's come down and consolidate some of this stuff a little bit. Okay, here's my definition. This is very important. The equation of a line is the rule which the x and y coordinates must obey if the point is to lie on the line. This is very, very important, and it isn't just about lines or any geometric shape, any curve. Okay, any curve. So Descartes was about drawing geometric shapes and finding their equations. Okay, and so their equations now we're finding out the equation is always the rule which the x and y coordinates must obey if the point is to lie on the line. How do you line them all up? Or how do you get a circle maybe? That might be an interesting one for you. How do you make points all lie exactly the same distance from a fixed point? That's one for the future, I think. That's an interesting one. But you need a rule, don't you? So that you can see if the points are going to form that geometric shape. All right, there's your definition. The equation of a line is the rule which the x and y coordinates must obey if the point is to lie on the line. Hey, aka, what makes the line straight? What makes a circle a circle? Interesting stuff. Let's go down and practice some things now. Okay, so here we are. We've got trying to find the equation of the line, and you can see what Pearson have done. They've used y1 and x1 as the known points here and used the general form. So let's take, we've got this and this in the first one. So the slope is y take neg 5 over x take 3. We're thinking about, remember, thinking about what's happening here. Let's just draw this a little bit. So we've got here 3 neg 5, let's say. I haven't drawn up a grid, but we've got 3 neg 5, and we know the line has a slope of 2. We want to know what the rule out here must be if that point's going to lie on the line. So what are we going to do? We say the slope is 2, got it. Now we'll work back here, y take neg 5 over x take 3. Must always be 2. No matter what the point is out there, it's got to keep that constant gradient or slope. Otherwise it won't line up. Okay, so then we multiply both sides by x take 3. Expand the brackets. They put y on the other side now. I mean, you might just take it this way. Y take neg 5 over x take 3 is 2. Why not start that way rather than having to change it around here? And therefore y equals 2x take 11. Let's do it the other way. You like mx plus c, let's go. Y equals mx plus c is your basic form. M is 2, so that implies y equals 2x plus c. And now, can we find c? Yes, we could substitute in the point. If that point is on the line, then we know it must obey the rule. So we will use the known point on the line to backtrack and find the rule. So y is neg 5 must equal 2 times x plus c. So neg 5 equals 6 plus c implies neg 11 equals c. Therefore the equation is 2x take 11. Same idea, bit different. We're backtracking to find c. We could just take it from the graph if we could see where it crossed the y-axis, but generally we don't know that, and so we have to use a known point and substitute its x and y in place there to backtrack and find c. Let's do the second one up here now, the gradient of neg 4 through a point neg 4, 2. So doing the same thing, neg 4 equals y take 2 over x take neg 4. Okay, and then multiplying across, putting the y on the left hand side here, and simplifying. So just look at that expansion, brackets first, neg 4x take 16, and then adding 2. Okay, neg 16 plus 2 is neg 14. So just check the algebra there. We've been doing a lot of that, so you should be okay on that. Let's have a look at doing it the other way. Y equals mx plus c. So m is neg 4. y equals neg 4x plus c. Substitute in a point to backtrack to find c. The point that we know is neg 4, 2. So therefore the y, stick that in place of y. Y of 2 equals neg 4, the x value, times neg 4. Remember, we're using the idea that if this point's on the line, then it has a rule that the x and y coordinates must obey to keep the line straight. So 2 equals positive 16, is it? Negative times negative is positive, plus c. So then subtracting 16 from both sides, neg 14 equals c. Let's put the equation together again now. Y equals neg 4x, take 14. Same answer both ways. Okay, so one is the slope-intercept form, that's y equals mx plus c, and using the general form in the other way. So I want you to try to do some of these both ways. Let's get our skill level up here and be very flexible with the way we're thinking about the equation of a line. Okay, remember, the equation of a line is the rule that points on the line must obey if the line's going to be kept straight there. Okay, let's come down. And here we have a few questions. I think we'll just come to there, and you can have a go at those equations. There's more coming up later, and we've got the answers over here. So try not to look at those for the minute, and just work through. Can you do both methods, please? I'd like you to try both methods in finding these equations. Okay, on each one. So you've actually got effectively 8 problems there. 4 problems done both ways. Okay, you might pause the presentation now and have a go. And then what we're going to do is to come on down and have a look at the rest of it. All right, let's go down now. Now I've got Pearson's textbook problems here all sorted out, so I'll just run through them and then we'll come back. So 3 and 4, and we've got the answers, and then 5, okay, and the answers, and then getting into the harder questions, and more in-depth understanding needed here for 6 and 7. There are our answers, and then 8. Interesting problem there, 8. And then the answers, and 9, 10, 11, 12, and the answers, and then open-ended questions at the end there. So you might have a look at all those. I'll take you back up to question 3 now. Just come back up to 3 and start there. 3 and 4. All right. So that's where I'm going to leave you. I hope you enjoy yourself there. We'll come back and do more in this area of maths, which is called coordinate geometry. So keep up the practice, build up those skills. For the moment, it's cheers from me.